Can chain-of-thought reasoning actually hurt a model's ability to recognize fine-grained visual details? At first glance, it seems counterintuitive. Chain of thought, or COTI, has become a cornerstone of reasoning in large language models. It's been shown to dramatically improve performance on math, coding, and logical reasoning tasks. But when it comes to fine-grained visual classification, a task that demands extreme visual precision, like telling apart two nearly identical bird species, or distinguishing between two car models with subtle differences, the story changes. Our research reveals a startling paradox: more thinking leads to worse performance. In fact, we've identified what we call the cost of thinking, a phenomenon where longer textual reasoning consistently degrades accuracy in fine-grained visual tasks. Let's unpack this. Fine-grained visual classification, or FGVC, is about spotting the tiny visual cues that define subcategories. Is that cat a domestic shorthair or a Russian blue? Is that aircraft a DC-8 or a Boeing 707-320? These distinctions aren't just academic. They're crucial for real-world applications in ecology, medical imaging, industrial inspection, and autonomous systems. Yet, despite the impressive capabilities of multi-modal large language models, or MLLMs, they still struggle here. And surprisingly, when we ask them to reason step by step, to explain their thought process, their performance often drops. We tested this across multiple open-source MLLMs, QN2VL, InternVL, R11 Vision, on 4 major FGVC benchmarks: Aircrafts 102, Flowers 102, Cars 196, and Oxford Pets. We compared two prompting styles: answer only, where the model gives a direct label, and chain of thought, where it must generate a reasoning trace before the answer. The results were consistent. COTI led to performance degradation across the board. For example, on the Flowers 102 dataset, QN2VL2B dropped from 54.8% accuracy in the answer-only setting to 51.1% with COTI. On Cars 196, the drop was even steeper, from 82.6% down to 56.8%. Even a dedicated reasoning model like R11 Vision, which is trained to think, underperformed when asked to reason. This isn't just a case of poor quality reasoning. We even generated high-quality COTI responses using GPT-4o and fine-tuned a model on them. Yet the answer-only model still outperformed the COTI version. So why does this happen? We took a deeper look, not just at zero-shot inference, but during reinforcement fine-tuning, or RFT. This is where the model learns from feedback, optimizing for accuracy over time. Here's what we observed. As training progresses, the model's reasoning length collapses. The average length of the reasoning text drops rapidly, from hundreds of characters down to just a few dozen. And as it gets shorter, accuracy goes up. This is what we call reasoning collapse, a self-regulating behavior where the model learns to suppress unnecessary or distracting reasoning, focusing instead on direct, accurate prediction. Why? Because during RFT, the model learns that longer reasoning doesn't help. In fact, it can hurt. The longer the reasoning, the higher the chance of hallucination, irrelevant details, or misdirection, all of which pull attention away from the actual visual cues. This leads to a key insight: the length of reasoning is the real problem. It's not that reasoning is bad, it's that excessive reasoning is harmful. The model benefits more from concise, focused thinking than from elaborate verbose chains. We call this the cost of thinking, a trade-off where the cognitive overhead of long reasoning outweighs its benefits in visual perception tasks. So how do we fix it? We introduce ReFine-RFT, a novel reinforcement fine-tuning framework that explicitly controls reasoning length while providing dense, accuracy-oriented feedback. ReFine-RFT has two core innovations. First, an ensemble reward system. Instead of relying on a single binary accuracy signal, we combine multiple rewards. Format reward ensures the output follows the required structure. Classification reward checks if the answer is correct. Thinking length reward encourages reasoning within a tight, predefined length. MLLM-based accuracy reward uses another model to score semantic similarity, not just exact string matches. Embedding similarity reward measures how close the predicted answer is to the ground truth in semantic space. Together, these rewards create a dense, continuous feedback signal that guides the model toward precise, accurate, and concise responses, without overfitting to exact wording. Second, multi-reward normalization, or MRN, a plug-and-play module that solves a critical problem in multi-objective training. Different rewards converge at different rates. Format rewards, for example, often saturate early, dominating the total reward signal and drowning out more meaningful signals like accuracy. MRN fixes this by normalizing each reward independently before aggregation. This ensures no single reward overwhelms the others, leading to stable, balanced training. The result? A model that learns to reason just enough, not too much, not too little, and focuses on what really matters: visual accuracy. We tested ReFine-RFT on all 4 FGVC benchmarks. The results are striking. On Aircrafts 102, ReFine-RFT achieves 79.3% accuracy, a plus 37% improvement over the previous state-of-the-art visual RFT. On Flowers 102, it hits 81%, a plus 69% gain. On Cars 196, it reaches 97.1%, a massive jump of plus 14%. And on Pets 37, it hits 88.6%, a plus 26% improvement. Even more impressively, ReFine-RFT achieves this with a 2 billion parameter model and only 4-shot training data, outperforming Findefix 8B, which was trained on the full dataset. And here's the kicker. Controlling reasoning length matters more than the prompt style. No thinking RFT uses answer-only prompts, while visual RFT uses COTI-style prompts, yet their performance is nearly identical. But ReFine-RFT, which combines both controlled reasoning and dense feedback, beats them both. This confirms our central thesis. In fine-grained visual perception, precision beats verbosity. So what's the takeaway? Chain of thought isn't inherently bad, but it's not universally helpful. In perception-heavy tasks, more thinking can mean more noise. The key is not to eliminate reasoning, but to constrain it, to make it efficient, focused, and aligned with the task. ReFine-RFT shows that by combining Ensemble rewards with multi-reward normalization, we can train MLLMs to be not just smarter, but more accurate, especially where it counts, in the subtle, nuanced world of fine-grained visual understanding. This isn't just about better models. It's about building systems that can be trusted in real-world, high-stakes applications. Whether you're identifying endangered species, diagnosing medical images, or inspecting manufacturing parts, accuracy is everything. And sometimes, the smartest thing a model can do is think less and see more.